Hello everybody. Let us resume our discussion on blackbody radiation. We've said that the physicists idealized this body called blackbody and found a way of making this idealized body which will be kept at a given temperature T. And they said that they can measure this thing called the spectral radiance for a blackbody. Then they observed, then they measured the properties, the spectral radiance. It turns out to be independent of the cavity to make the black body, independent of its material shape. And if the cavity is large enough, if the volume is large enough, then it is independent of the volume also. The total radiation was proportional to the fourth power of temperature, and it had these spectral signatures. We talked about Plancks Law. And finally, we said that, okay, so now can we explain the blackbody radiation using the known physics, namely the classical electrodynamics, which is the physics of radiation, and thermodynamics. And we saw that, okay, so if I use classical electrodynamics, then the cavity walls, at the cavity walls, one should have nodes of this electromagnetic wave. And from that, we can say that if we can measure the number of waves at a frequency range nu and nu plus d nu and the average energy in each of these waves, then I can calculate the spectral radiance in this following way. And that's where we stopped. So we also made the comment that nu comes from complete geometrical consideration and epsilon bar comes from the thermodynamics. So now today we will try to measure these two quantities or try to evaluate these quantities from our knowledge in physics and see what are the atoms made and what modifications are required in the known physics. The first atom was made by Rayleigh and Jeans. So before we go into that, what is common in all the atoms is calculation of this n. So let us first do that. And for doing that, we will first assume that what is an one-dimensional cavity. Because it is easier to calculate for one dimension. Okay, so we are dealing with a one-dimensional cavity, and the question we are asking is how many waves or number of waves. So let's write number of waves with wavelength greater than lambda. Okay, this is the number we want to calculate. Now, as we said, so let me draw for you the walls of the cavity. We'll consider, say, maybe 3 or 4, 3 maybe, 3 cases. So these are the walls of the cavity, and the cavity walls is at the linear distance is L. So L is the size of the cavity, one-dimensional cavity. Okay. So we said that the largest wave that we can have here, so if lambda, which I am writing here, is lambda 1, that is the largest wave can just have these half oscillations within this cavity. So for this lambda 1 is given by 2 times the L, right? Because this is half of the wave, the other half will give you total lambda. So here I get the number of waves is equals to 1. The number of waves I can get which is greater than lambda 1 is equals to 1. So let me rearrange this a little bit so that I can write it properly. So here I will write, here I will write number of waves. So number of waves, which is wavelength is equals to 2L, I can have only one such wave in the cavity. Then what can I have? I can have like the full wave fitting in here. So I will say that lambda 2, if that is lambda 2, then if I say that number of waves with wavelength greater than lambda 2, well, I can have lambda 2, I can also have lambda 1. So lambda 2 is here, of course, equals to L. So such waves, so I can write this as 2L by 2 also. Such waves, I can fit in two such waves. And if I consider the case where it completes 1.5 oscillation, which is, this is, now I am asking how many number of waves that I can fit in, which is having wavelength greater than lambda 3, which is 2L by 3. And you can see that I can fit in all these three waves here. So I can fit in three waves. So this way I can go on, but you have got the trend that number of waves with wavelength greater than lambda, one can support, one fit in, one can support is a better word, in the cavity of length L. This is given by n equals 2L by lambda, right? So the number is sitting in the denominator over here. So you can see the number is 2L by the corresponding lambda. In terms of frequency, I can change this in terms of frequency because we always are working in frequencies. So we can ask the question, number of waves with frequency now less than a given frequency, because greater lambda means lower frequency, they are inversely related. So this is equals to n is 2L by, and lambda we know is c by nu. So this is just 2L nu by c. Okay. Now let's say that we consider the case, we consider lambda much less than L. Okay. So what do you mean by lambda much less than L? I mean that I am only considering those wavelengths. We'll try to calculate the irradiance of, or the spectral radiance of those wavelengths which are much less than the size of the cavity. And that makes sense because you see that we said that the spectral radiance is independent of the volume of the cavity only if the volume is much large compared to the wavelength. So in that case, if I look at n here, this corresponds to a large frequency. And if I ask you what is delta n by n, well, n is, frequency is large, lambda is small, means frequency is large, means n is also large. Delta n is the change in n in successive n is an integer, delta n is always 1, n being large in the denominator, delta n is always 1, this tends to 0 as nu tends to very large, right? So here, because this tends to 0, I can consider n like a continuous variable when n is very large, right? So let's draw here a line. This is nu, and nu, this is one dimensional, so nu changes, say, along this line, and say I have also n which changes along this line. They're proportional, so we know that n changes with nu by this, which you have just written over there. Same thing, I just write it once more. So I ask the question, how many waves are there between a frequency nu prime and nu prime plus delta nu? Well, if it is a one-dimensional case, we are asking number of waves between nu and nu plus delta nu, or nu prime and nu prime plus delta nu, this is nothing but the n nu d nu for one dimension. And that you can easily see that in one case I have to write nu prime plus delta nu in place of nu and subtract from there by writing nu prime. So this will nothing but be d. If I write it as d, and differential is 2l by c d nu. Okay, so this quantity n nu, in this particular case, n nu becomes, n nu is essentially 2l by c. Okay, so this is in one dimensional only, in 1D. But we are to deal with a 3D cavity, three-dimensional cavity. We have to deal with a three-dimensional cavity, that is the real world. And remember that the spectral gradient doesn't depend on the shape of the cavity. So I assume that the geometry is such that the cavity is a sphere. So just like we are asking here that what is the value of n between nu and nu plus d nu, here, because it's a spherical cavity, I can use spherical polar coordinates also for spherical cavity. So here it is more like, I think of one sphere of radius nu and the other sphere with radius nu plus delta nu, and I ask the question, how many number of waves will fit in these two spheres? Okay, and you know that number, that if corresponding to nu I can write n, and corresponding to nu plus d nu I can write n plus dn, because nu and n is just proportional to each other, and the number of modes that will fit in is the area of this annulus region in terms of n, so it is 4 pi n squared dn. This you can directly get from your annulus area example in the spherical polar coordinates. But you see, there is a catch here. This n is always greater than 0. I cannot say that there are -3 modes fitting in the cavity, or -3 waves fitting in the cavity. That is a meaningless statement. So here, like if I consider this as my xyz axis, all my nx, ny, nz, if I consider a complete sphere, can go both positive and negative. There is a negative axis here, and there is a negative y here, and there is a negative z here. But for my integer numbers, which is giving me the number of waves that can fit in, can only be positive. So out of 8 quadrants in this, only the quadrant where both x, y, z are positive, I have to consider only those. So the number of modes which can fit in is actually given by this. And we know that n is given by 2l by c nu. So I can now write down number of waves that can fit in, or that have frequency between nu and nu plus d nu. This is essentially what we called n nu d nu, and this is given by 1 by 8 4 pi. N is 2 pi by L, sorry, n is 12 by c, so n square is 12 by c. I'm just converting this, 12 by c whole square, and then 12 by c, and this will give me 1 nu, this will give me d nu, so nu square d nu. Okay. But there is one more catch. The catch is coming from the properties of the electromagnetic waves. So let us discuss it a little bit here. You will learn it in the next semester in detail. So if a wave is going in this direction, so let's call it z direction, the electric field of the wave is a vector. It can have a component along x, and there can be a x component of the wave, which I say like this, which you are talking about. But at the same time, it can have a component along y also. So with the same frequency, I will have another wave which is along y. And these two waves are independent of each other. They are called polarizations. So there are two polarizations. And because there are two polarizations, I get a factor of 2 here. Okay. So because nx, ny, nz all greater than 0, I get this factor of 1 by 8. And because there are two polarizations, I get a factor of 2 there. So if I now write down the expression for n nu, I can now have everything here. So this 4 cancels, 4 and 2 cancels with 8, and finally if you do this, you get 8 pi by c cube L cube times nu square. So this is the expression which is coming for the number of waves between nu and nu plus d nu. Okay, so now that is out of the way. That is out of the way because this is one of the ingredients to calculate the RT, so that we have calculated. It came from almost completely geometrical considerations and some electrodynamics. We need to now calculate the average energy. So we need to now calculate the average energy per wave when the radiation is at a temperature T. If I can calculate that, then I can multiply these two to get the spectral radiance. Okay, so now we will calculate this quantity. And the first attempt was made by Rayleigh and Jeans. So the first calculation we will do is by Rayleigh and Jeans. And we'll see if we get the right result. Now, to do this, we need to have some idea about statistical mechanics and thermodynamics. So let me give you that idea so that you may have not read before, but we can introduce it here. So there is a thing called a Boltzmann factor, and these are all for things in thermal equilibrium. So what is the Boltzmann factor? It gives you the probability density of having an energy between, or if I am writing probability density, it's at epsilon for temperature T. So if the system is in thermal equilibrium at a temperature T, this gives you the probability density of having that energy. And what is this? So this is given by total probability is always 1, and you can check total probability. I will be able to figure out if I integrate it over all energy, so that you can check will be 1. Now this is used to calculate the average energy. The average energy is written this way. So it's epsilon bar. It's the same average energy that we are talking about. So the definition is this. You integrate over, this is integrate over 0 to infinity, epsilon, then p epsilon. So probability of having that energy is p epsilon, and then you multiply by that energy. So this is the average energy formula. Okay. So if you plot this, so what I am plotting here is epsilon times p epsilon. See, p epsilon has e to the minus epsilon by kt. So for very large epsilon, it will be 0. At epsilon equals to 0, what I'm plotting is multiplied by epsilon. So at epsilon equals to 0, it is 0. So this also looks somehow like the Planck curve, but it is qualitatively looks same, but it's a different curve. Okay, so this is the thing. And now I can just do this integration and calculate the average energy. That's what Rayleigh and Jeans did. So the average energy, if I do the calculation, is essentially p epsilon I have to put in. So p epsilon is e to the minus epsilon by kt. Kt is just a constant. So kt is in the denominator like this. 0 to infinity epsilon e to the minus epsilon by kt d epsilon. I know you should be very good at integration. So if you calculate the average energy, it will just come out to be kt. It is independent of any temperature. It is all temperature, it is same. It's kt. Okay. And now, because I have the average energy as calculated by Rayleigh-Jeans, and I have the number of waves in between nu and nu plus d nu, I can now calculate the spectral radiance. And this is calculated by Rayleigh-Jeans. So I say Rayleigh-Jeans spectral radiance. So I write this with Rj and on top. So what will this be? So kt times n nu, and then what else do I have? I have c by v epsilon bar. So let us put everything here. So you get C 8 pi by C cube L cube nu square. V is volume is again L cube, and I have KT. So if you actually calculate out Rayleigh's spectral radiance at temperature T is 8 pi by C square KT times nu square. So it is proportional to nu square. It's like parabolic dependence is there. And this is supposed to be the blackbody spectral radiance. So let us plot how it will look like with respect to the non-observed blackbody curve here. So I'm plotting here is R nu, RT as a function of nu. X-axis is obviously nu. So the blackbody curve looks like this, which falls down at large frequency. This you can see it's monotonically increasing with nu. In fact, it will go like this. So this is Rayleigh's. This is the observed blackbody. And as you can see, it is clear from both the plot and the expression here. This quantity at nu tends to infinity goes to infinity because it's proportional to nu square. Also, if I calculate RT, which is the total radiance integrated over all frequencies for Rayleigh-Jeans case, the integration is from 0 to infinity, and you have nu square sitting over there. So this also diverges. So at high frequency, both of these diverges. This obviously this explanation failed. It did not follow the blackbody curve. So this phenomena was called ultraviolet catastrophe. So what you learn from here, you learn that at small frequencies the Rayleigh-Jeans works fine. At large frequencies it doesn't. Bring the blackbody irradiance to 0, it fails at large frequency. So small frequency RJ works, large nu it fails. Okay. So at this point you needed a new explanation of the blackbody phenomena, which came from Max Planck. So now we will discuss Planck's theory of blackbody radiation, or Planck's law of blackbody radiation. So Planck realized the following things. First of all, the spectral radiance to be calculated multiplying n with epsilon bar. Epsilon bar depends on the temperature. In case of Rayleigh-Jeans, it did not depend on frequency. This is a geometrical factor. This comes from physics, thermodynamics, and etc. Second observation we have just discussed, nu tends to 0, or should I write this way, average epsilon is supposed to be kt because Rayleigh-Jeans work there, and Rayleigh-Jeans tells you average epsilon is kt. Limit nu tends to infinity, what should be the average epsilon or average energy? Well, see, n nu depends on n as a function of nu depends on nu square. So at large nu, if average epsilon goes to 0, then only the black body will go to 0. So this has to be 0 at large nu. So Planck hypothesized the following thing. So he said that at the cavity walls, when the radiation fall, the following things happen. The radiation sets, there are atomic oscillators in the cavity wall. It sets the atomic oscillators in the cavity wall in oscillation, harmonic oscillation. Then these atomic oscillators radiate and give back radiation. So what's happening? So I have, say, this is my cavity wall. Some radiation falls into it. The atomic oscillators in the cavity wall start to oscillate, and after some time, so they will radiate back. So that's how the deflection is happening. Okay. Further, you said that for this to happen, this energy exchange between the cavity wall and radiation requires some minimum energy. Okay, so if the energy is only more than that, then this exchange will happen, and that minimum energy is integral multiple of, or sorry, it's multiple of the frequency of the radiation. If the frequency of the radiation is more, the minimum energy required for this particular transition will be more. And the last point is that the total energy exchange at frequency nu, because it requires minimum delta epsilon amount of energy, which is h times nu. So total energy exchange So if I call it delta En, or okay, so let's call it delta En. So this has to be integral multiple of h nu. Okay, so n is an integer. So this is what Planck hypothesized. He observed these things happening and then he said that maybe this is what is happening. And so this is how physics progresses. You have to hypothesize something to explain something. So this is the celebrated Planck quantum hypothesis. Saying that the energy exchange, remember energy exchange only happens in integral multiple of h times the frequency of the energy. H is Planck's constant. Okay, let's see. So there are two things here. One is that the energy exchange will not happen if the energy is not delta E. It has to be greater than that. The other is that the total energy, when I want to calculate, then I have to consider that the energies are in discrete steps, because the energy exchange happens in discrete steps. Where will this be important? Well, it will be important here. You see, now I cannot do it as an integral anymore. I have to do it rather like a summation, because integral considers all possible energies, but now my energies are in steps of h nu. Okay. One more thing that I have to remember here is how I got this kt. This kt is essentially 0 to infinity d epsilon e to the minus epsilon by kt. Okay. So that is what is sitting in the denominator, and I have to consider that changing into a summation also. So let's try to understand it a little further before you actually calculate the average energy. You see, we are plotting these curves where x-axis is nu, y-axis is epsilon times p epsilon. Okay, and the curve looks like this. P is e to the minus h nu by kt, so the curve will look like this. And what is the integral of epsilon p epsilon d epsilon? Well, that's nothing but the area under this curve. This is the area under this curve. Now, given a temperature kT, I have a frequency here which is, okay, so this x-axis is not frequency, this x-axis is E, right? This is epsilon. So given a value of temperature, I have an energy kT which I can level like this. I wanted to use this. Okay. I can level like this, right? Now consider the case which is nu tends to 0. Nu tends to 0 means the energy, smallest energy that is of consideration, which is h nu, it will be considered less than kT, so that delta epsilon lies somewhere here. Okay. So you see, one effect, as we said, is that we have to change the integral limit when you calculate the average energy so average energy was this, from 0 we have to change it to delta epsilon. So what happens is when nu tends to 0, delta epsilon is here and kt is somewhere here. So delta epsilon is less than kt. So I change the integral limit. Let's say that we are still doing the integration, not a summation. And in that integral limit, so I am considering this entire area. Now this entire area is almost the total area. Total area means if we have integrated from 0 instead of starting from delta epsilon, I would have got almost the same area. So because of that, the epsilon bar does not change. So epsilon bar, even if I change this integral limit 0 to delta epsilon for nu tends to 0, the epsilon bar remains the same. So because of that, for nu tends to 0, you still reproduce the Rayleigh-Jeans formula reproduces the blackbody spectrum. But what happens if I have nu very large? So I'm plotting epsilon this again here, and this is the epsilon curve, and say again kt now somewhere here, and we are talking about nu tends to infinity, which is nu very large. So delta epsilon, which is h times nu, will be much greater than kt now. So delta epsilon will be somewhere here. And now you see, if I start my integration from delta epsilon, I get only this much of area, and as delta epsilon goes to the right hand side, as it increase nu, that area is almost 0. So epsilon bar goes to 0. And that's what we expected, and that is what we wanted to happen, for such that the Planck's radiation formula we get at very large nu. Remember that Planck's radiation formula gives us 0 at very large nu. That was not seen, and what we saw was ultraviolet catastrophe. But it seems that we'll be able to reproduce the Planck here. Sorry, I'm saying Planck's radiation formula, but what I mean is we will be able to reproduce the blackbody radiation observed curve here. Okay, so now how we'll have to calculate epsilon bar? Remember, we have to do two things. One is we have to change everything to summation. So in the summation, so I have to start with n equals to 1, and the energy for n equals to 1, let's say epsilon n, and here again n equals to 1, the upper limit can be infinity, you can have as large n as you want, and this is epsilon n times e to the minus epsilon n by kt. And epsilon n, just from Planck's quantum hypothesis, has to be nh nu. Okay. Now I'll not do the calculation. This is your homework. To get from here to here, that epsilon bar, if you calculate, put nh nu over there and do the summation, what you will get is h nu by e to the h nu by kt minus 1. So this is the average energy that you calculate using Planck's radiation formula. I'm sorry, using Planck's quantum hypothesis. And you can check, again homework, that limit nu tends to 0, epsilon bar as put from there, this will come out to be kt, which is at limit small frequencies, this goes to the Rayleigh-Jeans limit. So this, now let us calculate the Planck, or let us write down the Planck blackbody radiation formula. So the spectral radiance is, if you put in everything now with the newly calculated epsilon bar, you will get this. And this matches exactly with the observation. And that was the success of Planck's quantum hypothesis. So he hypothesized these things, how the exchange of radiation happens. It happens in discrete way. So there is a minimum exchange that is possible, which is given by h nu for a given radiation of frequency nu, and all the exchanges are integral multiple of that. Once he assumes that, he can explain the blackbody radiation curve as it was observed. Now, as we said, that all this calculation assumes that the cavity that you make is very large compared to the wavelengths that you are observing. You may have heard of something called the Big Bang theory of the universe. In that, it is expected that the entire universe will behave like a black body which has a present temperature of 2.732 Kelvin. Okay, this is a measured value, obviously. NASA in 1990s sent a satellite to measure the blackbody spectrum. Now, when you do any measurement, you get to measure it at some discrete values of frequencies. So maybe these are the points that you measure. Okay. Now, whenever you measure a point, you also always, there is an associated error in that measurement. It's a very important thing, or probably the single most important thing that you will learn when you start doing experiments. After you come here, and you have to put the error bars, which tells you how much error is there across that particular measurement. It can be different for different measurements at each of these. And when you are trying to verify a theory like Planck's law here, what all you have to see is that when you plot that Planck's law, in this case for say that's 2.732 Kelvin, which is the temperature of the universe if you wish, then this curve goes through all these error bars. If it goes through all these error bars, not these points, you are happy enough. Okay, so this radiation has a name called cosmic microwave background radiation. And I request you to figure out why it is called microwave. The answer is already given in these two lectures, but I'll not tell you precisely where is the answer. So try to figure out why it is called microwave. Half of the answer is there in this, what you can see in the board right now. What happened is that, see, it's the entire universe working as a black body. The universe is the largest cavity that you can make in the universe. So because of that, this is the most precise black body that one sees. And how precise it is? Well, when they plotted this error bars and the point, and first they plotted the points, tried to fit the black body spectra, and they get a very perfect fit. All the points, this curve goes through all the points, and then they realized that it is so precise that these error bars are extremely small. They had to be magnified 1000 times even to see them. So you can imagine how perfect a black body the universe is. So one Planck's radiation hypothesis, Planck's hypothesis, which is about the exchange of radiation, explained this new phenomena. And you see that he has to take that new hypothesis to explain it. So that we will carry on, and we'll see what else we have to more hypothesize such that we can explain some more odd phenomena that we started to see at the beginning of the last century. Thank you.